So thank you very much to the Children's University and to all of you young people right across the UK. It's brilliant to be with you. Now, let me just share my screen so I can tell you a bit about what we're doing for the next little while. And hopefully this will all work, he says, and the technology is there. There we go. So it's great to see you. As Louise has indicated, or you've seen in the publicity material, my name is Professor Robert Walsh. I'm at the University of Central Lancashire in Preston in the northwest of England. I don't know if you've ever been up to Lancashire. We've got Blackpool at one side, and then we've got Manchester the other, and somewhere between we've got Preston, which is where I am, and I work in the Jeremiah Horrocks Institute for Astrophysics and Mathematics. But also, there's a big organization which stretches across our entire world, and it's called the International Astronomical Union. And basically it brings together astronomers and scientists and educators from right across the world, from about 80 to 90 countries, in order to use astronomy to help to understand the world around us, of course, which is what we're doing today, but also trying to push forward research and programs into understanding outer space. And they've got a special program happening over this weekend. Where you're having 100 hours of astronomy, where every hour there's an activity taking place, and you are part of the UK part and section of this. I represent the UK as a National Outreach Coordinator, which means that if anything comes from the International Astronomical Union to the UK, I'm the one that they speak to, and then I pass it out to organisations like Children's University. So that's what we're doing today and the program we're doing. And you can go onto the IAU 100 Hours of Astronomy website, type that into Google or a search engine, and you'll see all the other recorded activities that's happening right across the planet. But the little talk we're going to be looking at today, and the things we're going to try and do together, and I want you to have a think about, is the hopefully exciting title of Storms in Space. What it means for our planet connected to our star, and what the term is space weather. We talk about a lot of the weather in the UK, don't we? And this is not just weather on our planet and weather in our country, or even weather along where you live in your city or village or town or region. This is weather out in space. Now, I'm fortunate with the work that I do, that I get the opportunity to work with NASA, the American Space Agency, and I'm going to show you bits and pieces of that NASA work, and particularly about space weather today. Some of the things I do include this. So that's something called a sounding rocket, launched from White Sands, New Mexico. And at the top of that rocket is actually an instrument, a very specialized telescope, which we took years to make, and then you put it on top of a rocket. And that's because we need that instrument, that telescope, to be in space. And that's the sort of thing that I do to try and understand our star. So this is maybe an image of you that you would maybe think of when you think about the sun. You know, we go on holiday, if we, you know, during the summertime. Maybe this time you went this last summer throughout the UK rather than to other countries across the world for obvious reasons. But you've been going somewhere to try and enjoy the sun, to go and paddle in the sea, or go and go on walks or trips, or simply to try and enjoy yourself in the sunshine. But what is this ball and a bright ball in the sky, and how does that, I suppose, affect us here on Earth? Why do we do the things we do in relation to this sun? It's been the same throughout history, actually. If you go to different cultures and different countries, they've sort of realized how important the sun is. You know, the Greeks had the name Sun Apollo. The Aztecs there were involved. China, it's called 10 suns. Even in Japan, you've got Amaterasu. All different names for this object in the sky. It's its daily arrival being praised, but the nightly departure of the sun sometimes making people very afraid. But what is it? And how important is it? And why are we sitting here today for a short period of time trying to understand it, and why the science of the sun and space weather is important to us? So what is it? Well, here's an image from the Hubble Space Telescope. And it's a telescope, funny enough, that's in space. And the Hubble Space Telescope has revolutionized, completely changed our understanding of the universe around us. This image is about the size of your thumbnail. So if you went outside and held your thumb up against the sky, then the size of your thumbnail is a patch of sky that Hubble was looking at here. And you can see big galaxies, which are collections of stars, but also you can see little pinpricks of light. And then that individual stars, there are also galaxies that are just very, very far away. You know, we'd estimate that there's about 10 billion galaxies. That's 10,000 million galaxies in the observable universe. And every galaxy roundabout has about 100,000 million stars. That's an awful lot of stars when you put them in all those galaxies. In fact, it works out to be about 1 billion trillion stars. And I'm only going to tell you about one of them, this one, our sun. And why it's important is because it's the star that's closest to us. It's our star, the star we move around, and the star that we rely upon for all the heat and light and energy for life on Earth. Now, this is really what your sun looks like. I'm going to show you a couple of these little movies and bits and pieces like that, but this really is what the sun looks like from space, from a special telescope that we work on at the University of Central Lancashire. So there's no cartoons. This isn't sort of Avengers Endgame or anything like that there in the CGI. This is really what the sun looks like from space. So what's the stuff of the sun then? If that is the sun, and if that really is, what's the stuff of the sun? What's the sun made of? Well, I've got something here I want to show you. And I need to switch the lights off in my office here to do this. There we go. Hopefully that'll help a little bit. It's still a bit bright, but hopefully you'll be able to see. There we go. Do you see that okay? There we go. This is what is known as a plasma ball. And inside this glass sphere, there's an electrode, it provides electricity, and then the gas inside it, it's probably argon actually, gives you the opportunity for the electricity to flow through the gas and out to the edge of the sphere. You can actually touch this. Here we go. You've got this before. If I was in your classroom, I'd be letting you touching it, and you can see it tries to follow your hand over for what's going on. It's trying to actually get down towards the earth, really. You can put your nose against it as well. Ah! No, it's okay. Don't worry. It's fine. But this stuff inside here is known as a plasma or an electrified gas, is essentially what's in the sun. So a bit of different in regard to the temperatures, but the idea behind what we see here is what we see and what we have in our star. So you can go get one, if you like one of those, you can buy them at shops and famous online stores whose name I won't mention, but you can go and get a plasma ball for yourself. A lovely, lovely demonstration of science, and particularly about electrified gases and, of course, about the sun. Now, if that's what the sun is made of, and that's the sort of, it is a star amongst all the billions of stars out there, then whereabouts is it? Well, you may think that's a bit of a daft question because you look up at the sky and there it is. But where is it relative to everything else that's going on in our solar system, if not our entire galaxy? The galaxy which our star is in is known as the Milky Way. And this isn't the actual Milky Way. This is just a diagram to show it because we can't travel out of the Milky Way and look back at it, though we can look at similar Milky Way type galaxies around us, which tell us, well, maybe that's sort of where and what our Milky Way galaxy looks like. And where the arrow's pointing there is where we think the sun is, not at the very center of the galaxy where there's a big black hole, but rather just out towards the edges of the Milky Way. And somewhere which is actually quite good because there isn't a lot of activity, a lot of exploding stars or anything like that going on. Now, here we have a picture of our sun to the left, and then all the planets after it. And of course, we are on the third planet, Earth. This is not to scale. This has all been squashed down so you can see all the planets in the order as you would travel out from the sun. The distance between the sun and the Earth, that's the third planet there, is about 150 million kilometers, 93 million miles in old terms. It takes light, which travels from the sun, about 8 minutes to reach us here on Earth. And light is the fastest thing in the universe. It does mean when you glance up at the sun, don't look directly at the sun, but if the light you are getting from the sun at this moment in time in your classroom actually left the sun 8 minutes ago. Not just right now, but 8 minutes ago. You're looking, in some respects, back in time. So here's all the planets. We've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And I'm sure you've learned the planets and learned the ordering of the planets. And of course, the important thing is the sun and us. Why does it work? Why is our planet in this location, in this place, in this neighborhood of our solar system, and why is it important? Well, let me give you an idea. This is all the planets at the right sizes on one slide, on one picture. And maybe you knew that Jupiter, the planet with a big red spot, it's the big one, it's the biggest planet. Then Saturn, with its lovely rings around it, is in second place. That's my favorite planet, really. Well, did you know that Uranus and Neptune are much, much bigger, in third and fourth there, than the Earth, which is in fifth place there, just outside the Champions League places. It's playing in the Europa League. So that's what the Earth looks like compared to the other planets. If I add the sun in, it's very different. Look at the planets down there in the bottom right, small. You can hardly see the Earth compared to our sun. And the sun is a bit of an ordinary star, really, but look at the size and scale compared to our planet. You can fit 109 Earths across the diameter of the sun. You can fit 1.3 million of our Earths in the volume of that sun object. So you can see how important it is. It's a gravitational center of our solar system, and all the planets go around it, including our own. So here's a little thing. I always try to remember the ordering of the planets when you travel out from the sun. You may have different sentences or different sort of phrases that you use. I like to add the sun into that list, so not just the planets, but also the sun. So here, the phrase that I use to remember is, sometimes my very easy method just speeds up nothing. So why would I do that? Well, every capital letter helps you to remember what the ordering of the planets out from the sun are. So sun is sometimes, Mercury for my, Venus at very, Earth, that's easy, Mars method, Jupiter at just, Saturn is speeds, Uranus is up, and Neptune is nothing. So sometimes my very easy method just speeds up nothing. And maybe you can make up your own list of phrases to help you remember what the planets are, of course, but also what the ordering of the planets are from the sun. Now, if we think the sun is so important, it's so massive, we think it's about 98% of the whole of the solar system is all contained within the sun compared to the planets, and even less in our own world. How do we look at the sun? How do we observe it? How do we examine it? How do we even investigate it? How do you do something like that? Here's an image from Preston, which is where I live. We have a dock area, Preston Docks area, which is lovely water you can walk around. And this is a lovely sunset picture taken by someone here in Preston. And, it's, what is that thing out there? How do we actually observe it? You don't want to look directly at it because that would very much affect your eyes. Like they say it again and again and again. It's so important. Never look directly at the sun. You will damage your eyes, and never use a telescope or binoculars to do that unless they have very special sort of covers or filters on them, which help to block out a lot of the light. A lot of amateur astronomers would have that, or professional astronomers. It's not something you would usually have, so be very, very careful. Now, you can't look directly at the sun, but actually there is a circumstance where something actually happens, which is only here as it happens on Earth, which helps us to really look at it. And that is something known as a total solar eclipse. Now, this is where the fact that the Earth is going around the sun, but of course we've got the moon going around the Earth. And the fact that the moon is just the right size and just the right distance from the Earth at just the right time, it blocks out the bright bits of the sun and casts a shadow right down onto our world. It happens sort of every year and a half, 18 months or so. And it's a beautiful thing to experience. Maybe there's someone out there in the classrooms, in the schools across the country who are here with us this afternoon, and maybe you've seen a total solar eclipse, or maybe your teacher has been to one, or maybe somebody you know in your family or those who look after you have been to see a total eclipse. I was fortunate to see one in a couple of years ago, in 2017, and this one went from one side of the United States. That's what the map is here. This is America on a sort of Google Maps type of diagram, and the pathway going from top left to bottom right there is the path of the eclipse as it swept across the country. Maybe there's somebody who's here today who's able to see that. It was quite an experience, really. And I was in a place called Carbondale, Illinois, which is a very, very small town in the middle of America, because that was the point where you could see the eclipse best and for the longest period of time. It was only a few minutes. Some eclipses last for about 7 minutes. Some of them can last only a few minutes. We were at the few minute stage, but it's still amazing to see. Let me show you some of the photographs that I took, because it gives you an idea of that connection with the sun. So, we again had a special filter on our camera here, so we're not looking directly at the sun. And you start to see the moon moving in front of the bright disk of the sun. It's like taking a slice out of it. So this isn't like you would see the moon at night. This is the sun with the moon moving in front of it. And then eventually the moon covers the disk of the sun. And you get this bright halo around the sun, around the moon, and that's the outer bits of the sun. It's like a crown around the moon. It's called the corona. You can see there's some clouds out. Get to get a bit cloudy and things like that, but we're able to see it. It's like a big hole in space, really staring down at you. And the birds go quiet, the temperature drops. It is a very, very strange and unusual thing to experience. But if you ever get a chance, go and see a total eclipse. It's an amazing thing. And we're very fortunate on Earth that we can see it. None of the other planets in our solar system experience anything like it. Now, of course, if you want to look at this, I'll say again, never look directly at the sun. You will damage your eyes. And particularly for solar eclipses, it's better that you actually wear these eclipse glasses. And I've got a pair here today. And usually I bring these to classrooms and you can get an idea what's going on. But if I wear them, I can't see anything, which is good because you want to block out your eyes. So don't be like this gentleman. Here's the President of the United States at the time who did look at the sun, and we were basically telling them not to. So don't be like that. Be like my son, Matthew, and my daughter, Emma, who were with me in the States wearing their eclipse glasses and actually protecting their eyes. Here's what NASA took of that picture. You think my pictures were sort of okay. If you zoom away in your very, very special cameras, this is what it looks like. And here's the outer bits of the sun stretching out into space with big rays of this plasma, this electrified gases flowing out into space, flowing in our direction as well. And it tells us another bit about the sun, and that has to do with magnetism. The fact that the sun is actually a magnetic star. And I'm going to show you some magnetic experiments in a moment to try and describe this to you. Now, we don't have to simply wait for an eclipse to see the sun in this way. We now have all these satellites that help us, a whole fleet of satellites that are observing the sun for us. This is the one that I work most on and has been known enough from NASA. It's called the Solar Dynamics Observatory. And you can see 4 telescopes there at the top of the satellite that's staring at the sun so we don't have to. And it's an amazing mission, really. Here's a little movie of what I've already shown you. This is a part of the atmosphere of the sun known as the chromosphere. Not going to go into all those details today. It's a bit beyond what we want to do. But you see the sun actually does rotate. It takes about a month for the sun to make a full rotation, move around on itself. And there's lots of eruptions and things popping out all the time. And that's the source of the space weather, which we'll talk about in a moment. You can also look at different parts of the light that comes from the sun. This is a slightly higher temperature. This is around about just over 500,000 degrees we see here. And there's all these things bursting out all the time. And the reason for that is a connection between magnetism and this electrified gas, this plasma that we're talking about. And the two can affect each other. And when they do, that's when the excitement really starts. You can go onto the NASA SDO website yourself. I took this image just a few minutes before we started the talk today. You can go to the website and you can see what your sun looked like just about 15 minutes before. So the satellite takes these pictures, sends them down to Earth. Some of them get put onto the website here, and you can see where SDO is around the Earth, but also you can see what the sun looks like right now. This one was taken at about 1 o'clock, so just about less than an hour ago. So you can go and see it yourself. It's in real time, and now we've got something that helps us to look at the sun so we don't have to. If you fly closer to the sun, really, really into the surface, and you take your telescope and you peer as quickly as close as you can, this is the sort of thing you see. This really is the edge of the sun. That curve in the middle there is the edge of the sun. And these big loops, these big arches that you see are due to magnetism affecting the gas that we actually see there. And in order to do that, let me switch off my camera and do a few experiments. Switch off my sharing and do a few experiments with you today. So I'll put my light back on it. There we go. What have I got? I got a couple of things here I wanted to show you. First, I've got this here, and I hope you can see this all right. Here we go. There we are. Now, what do you think this is a glass bottle. In this glass bottle, we have some clear liquid, but also we have this sort of black blobby stuff. Okay, these are what is known as magnetic nanoparticles. And that's a big posh word for saying that these actual, this fluid or liquid actually can get affected by a magnetic field. So here I have in my hand here, you see that this is a little tiny magnet, okay? And I'm going to bring the magnet up, and hopefully you'll be able to see that the material moves because I've got the magnet in place. Now let me see if I can get it over here so you can see it moving up. And if I turn it on its side, you'll see a very strange shape. Can you see that shape there? And that's due to the material. This liquid, these nanoparticles, actually being affected by the magnetic field. They actually like the magnetic field, and they line up along the shape. If I lift that off, it falls down. So it's all due to magnetism. So this magnetic field can actually move the material about and actually affect its shape. We see the same sort of thing on the sun. Let me show you another little experiment here to give you an idea. So I'm going to switch my camera to this one, and hopefully you can see that okay. What I have here, again, is another magnet. So here's a magnet here, and I've got a perspex, so a screen that it's sitting on. And I'm going to take some iron filings, little just metal filings, okay? So let's just see, you can see those. Not really, good idea. You'll see them in a minute when I take this and I start to spread this all over. So very, very liberally, a lot of it. Move these big bits out of the way because they don't help very much. Just try and spread it all over the place, okay? And you may think, well, it doesn't really do very much, Robert. Well, I'm going to hold the edge and I'm going to tap this. And you start to see the iron filings lining up against the, it's probably not as good actually, up against the magnet. Let me try and zoom in so you can see. Here we go a bit closer. There we are. You can see it lining up. Let's go a bit closer again. There we go. And what you're seeing here is the actual line, the shape of the magnetic field, the shape of the magnetism around the magnet being lined up to and being shown its shape because of the iron filings. They love to actually get connected to the magnetic field and follow its pathways. And so that's so you get an idea of what the shape is around the magnet by looking at the material, how you see the invisible magnetic field, just in this case, looking at the iron filings. Let me go back to my camera again. You can see my face, unfortunately for you. And I'll share my screen once again, because remember that picture, what we just saw there, and look at this. It's exactly the same thing, but it's happening on the scale of the sun. In fact, these arches, these sort of shapes, these curves that we actually see, this is that plasma, that electrified gas lining up against and showing the shape of the invisible magnetic field that's popping out of the surface of the sun. To give you an idea of size, that arch there at the bottom left, you could easily roll the Earth underneath. But the physics, the science, is exactly the same. So how does then this sun affect us? I've told you all about the sun and all about the materials. How do you get from the sun down to us? And why would you even care? Why would you even want to know more about this? Well, we're very fortunate where we are on planet Earth because we exist in something known as the habitable zone of our star. It's big words, which basically say that where we are, with the distance we are from the sun, is just right for water to exist on our planet. And as we look for other planets and other stars now, and we're doing that, we call those other planets exoworlds or exoplanets around other stars. One of the things we look at is, are these planets close enough to their star or not too far away from their star in order for there to be liquid water? It's a bit like the Goldilocks zone. We call this the Goldilocks zone because, the Earth in particular is not too close into the sun. It's not too far away from the sun. It's just right for these conditions to be perfect for life to take place. And even though we've been looking all over the universe now for different planets and trying to work out about life on other planets, we've only found one, and that's us so far. But the conditions on Earth are brilliant for us to know and to learn about and see. Maybe there are things around other stars too. But the sun provides all the light and heat and energy for this, our planet, where you live, and we've got to look after it. We've got to not pollute it. We've got to really look after our world because it is such a special place particularly for us, but just generally. In the whole universe, the Earth is very special. But we also have the fact that the sun does interact with our planet. It comes down and does strange things. As well as producing this light and heat and energy, there's also big eruptions or storms which come out from the sun and come our way. And examples is shown here. We've got one of a very special telescope which allows us to block out the bright disk of the sun and create essentially an artificial total solar eclipse. And here's an example here of that, where we block out the bright disk and you look in the same type of light that your eyes and my eyes are attuned to what's happening around the sun. And you see these big puffs, poof, 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 these big sort of balloons type thing coming out and going out in all directions. These are the solar storms which rocket out from the sun, often on a regular basis. The one that gets all the sort of snow towards us is the one that's actually heading our way, because the telescope here on this satellite is at the Earth looking back at the sun. So when you see those happening, then you know you've got a solar storm coming your way. So let me give you another example. This is one where you can actually see it on the sun itself. It just erupts outwards. And I've put the Earth on this image because the Earth's not really there. It's not as close as that, thank goodness. But it gives you an idea about the size of these. Billions of tons of electrified gas rocketing out of thousands of kilometers a second. And again, it's due to magnetism and the plasma twisting in upon itself and then throwing itself out into space. Here's one of the biggest ones we've ever observed in the last few years. And you can see this takes up nearly a quarter, if not a half, the size of the entire sun. We were fortunate this time that this eruption didn't head towards the Earth. It was pointed in a direction that missed our planet. But these things do happen, and we have to understand them and try and protect, particularly the technology we have against them. Here's a little cartoon to show you what space weather is really all about. So the sun's to the left, and our planet Earth is to the right. And this is not to scale, you know, it's 150 million kilometers. It's just to show you what's going on. But if one of these solar storms erupts and starts to head towards the Earth, it's usually about 2 to 3 days before it hits our planet. And of course, we have a magnetic field around our planet because we have our own magnetic core, iron core, which generates a magnetic field, which actually protects us here on Earth. Let me stop sharing and do another wee experiment with you. So to give you an idea about the magnetic field, and you probably use these if you've done any sort of outdoor experiments, or you do any hill walking or things like that. Maybe you're in the scouts or the guides and you would come across a compass. And compasses work because you line up, maybe see if I can actually get this lined up correctly. Here we go, against the north and south. There we go. And I know that when the arrow is pointing in, the red one is pointing in one direction, is pointing towards the north, and the green is pointing, the black really, I suppose, is pointing to the south. And that's because this is a magnetized little arrow that aligns itself with the Earth's magnetic field, just like our iron filings aligned with our magnet. This is very useful for us to find our way around. Number one. Number two is I've got these big magnets here. Okay, this is like a magnet you would get in, I don't know, Tom and Jerry, not Tom, well, Bugs Bunny or Roadrunner cartoons, which I'm showing my age out there, but some of your teachers will understand what that is. Acme magnets. And if you have a magnet, let me hold this one up for you. You can see, okay, so hopefully if you know magnets, you have different poles and they're opposite to one another. So here we have a north and a south, and every magnet, has a north and a south pole. Suppose I'm going to put a north, let me see where the north is. It's that one there. Okay, so I'm going to put the norths against each other and the souths against each other, and we'll see what happens. So we're going to put them up against each other, and I'm pushing it together, and I'm not messing about here. There is a force that's pushing me back. Ugh. You can't force them together. If you have two norths or two souths against each other, they repel. If, on the other hand, I turn my magnet over and I have a, what have I got here? A north against the south and a south versus the north, top and bottom, and I bring them together, then they attract. In fact, they attract so much that I can just hold it here and talk to you through the little hole. So you've got magnets, and depending upon whether you have north poles or south poles, then you either have they repel or they attract. Would you believe the same thing happens between the sun and these solar storms and us here on Earth? It depends on the solar storm that's in the cloud and what shape and what we call is orientation, or what direction it points, against the direction that our Earth magnetic field is. And sometimes they crash into our Earth magnetic field and they bounce off, they repel. Or if it's just right, they come in and they interact with the magnetic field, they crash into it. And the Earth's magnetic field wiggles backwards and forwards, it rings like a bell, really. And that's when the fun can really start here on Earth. One beautiful byproduct of this is known as the aurora borealis, or the northern lights. And here's where I often ask in classrooms, has anyone seen the northern lights or the aurora borealis? These are shimmering curtains of light, green and purples usually, for the oxygen and nitrogen atoms that are being excited because the material from the sun, this plasma, is hitting our planet, and it gets inside the Earth's magnetic field, actually, and excites the atoms in our atmosphere, excites the material in our atmosphere, the oxygen and the nitrogen in particular, and then releases all this energy in waves of light. So if somebody says, oh, look, there's green lights in the sky, go out and have a look at it and tell them it's the northern lights. It's not some alien invasion. It's a natural thing that's a consequence, what happens when a solar storm strikes our planet. But also, of course, we've got a permanent presence in space now with the International Space Station. You know, there's always been people up in the space station for decades now. And to give you an idea of the size of the space station, this is around the size of about 2 football pitches together. So it's a very big structure. And you wouldn't want to be an astronaut out on a spacewalk when a big solar storm is striking the planet. In fact, what the astronauts in the International Space Station do is they have to go to a sort of shielded part of the station, a protected part of the station, and in order to wait for the storm to go past. It's a bit like being in a fishing boat at sea with a storm coming towards you. You just sort of, as they say, batten down the hatches and wait for the storm to go past, because there's nothing you can do. You've got to make sure you simply ride out the solar storm. Unfortunately, satellites will also get affected by this, and they're not as lucky. They can't hide away. And sometimes satellites have been not sort of destroyed, but at least disorientated. They didn't know where they are. Maybe they got moved, or some of the fragile electronics got broken because solar storms struck the Earth. And we're still trying to work out how to stop the effects of these in satellites and other things. In fact, the UK now has something called a space weather sort of team that's purely looking at trying to understand how that space weather could affect us here on Earth. In fact, I'm part of a wider mission known as the European Space Agency Solar Orbiter mission. And this has just been launched, 18 months ago, something like that. And the thing about Orbiter is that it's different because instead of staying at the Earth, Orbiter is going to the sun. So it has a very special shield at the front of it, a very special heat shield, and it's going closer than Mercury into the sun in order to try and sample the the plasma, the electrified gases there, as well as actually take some of the sharpest images we've ever seen in order for us to understand our star, but space weather in particular. So I've given you a whistle-stop tour on storms from the sun, going from the sun itself and all the energy that's down towards the Earth and trying to understand what happens when it reaches us. I hope you've grasped a bit more about the sun, just like this guy here, which of course is an optical illusion, but I like it a lot because it's something about, well, can we grab more not just information about the sun, but actually try to understand how important our star is. And in order to finish and our time together, I'm just going to play a song to you. Now, I'm not going to sing, you were glad to hear, because that would put you off your lunch and everything like that. Rather, I want you to listen to this song from a band called They Might Be Giants. And it's all about the sun and about how the sun is a mass of incandescent, or rather, energetic, full of energy and life gas. Let's see what you think about They Might Be Giants.